Okay, welcome to chemistry. In this playlist, we're going to be going through the chemistry textbook shown here. This is Chemistry by Raymond Chang and Kenneth Goldsby. In this video, we're going to get started with Chapter 1. So, Chapter 1, Chemistry, the Study of Change. Chemistry is an active, evolving science that has vital importance to our world in both the realm of nature and the realm of society. Its roots are ancient, but as we will see, chemistry is every bit a modern science. We will begin our study of chemistry at the macroscopic level, where we can see and measure the materials of which our world is made. In this chapter, we will discuss the scientific method, which provides the framework for research not only in chemistry, but in all other sciences as well. Next, we will discover how scientists define and characterize matter. Then we will spend some time learning how to handle numerical results of chemical measurements and solve numerical problems. In Chapter 2, we will begin to explore the microscopic world of atoms and molecules. Okay, so it says we're going to begin our study of chemistry at the macroscopic level. So what they're referring to here is you have different scales, size scales. So a macroscopic scale is referring to a scale that we can visually see and touch and measure directly. Anything that we can visually see and analyze with our eyes without having to use some sort of special instrument like a microscope, that size scale is referred to as the macroscopic scale. So when you measure something with a ruler or a tape measure, you're not having to use some sort of special microscope or like a high-powered magnifying glass to analyze the size of that object. Yes, you're using a tape measure, but you could put the tape measure away and visually analyze the size of the object. The tape measure is just so you have some scale to reference, to put numbers to. If you wanted to, you could forget the tape measure and just kind of say, look, it's this is about 4 of my feet lengths long, etc. Okay, now the other common scales are meso, micro, and nano. All right, so micro and nano are referring to the metric prefixes, the micro and the nano metric prefixes. Micro is 10 to the minus 6, nano is 10 to the minus 9. So if the size scale of something is a million times smaller than the macro dimensions, 10 to the 6th times smaller, then that's a micro scale, like grains in metals or a lot of bacteria, or a million times smaller than a macro dimension like an inch or something, or a foot. So we can't see them with our eyes. We're going to need a microscope. And this isn't like a rigid definition. It's like you can't use a microscope to view something that's 10 to the 5th times smaller or 10 to the 4th times smaller than macro dimensions. It's just a general term. Okay. Now the nanoscale is referring to a billion times smaller, 10 to the 9th times smaller. So this is going to be on the order of the size of atoms. All right, now the mesoscale is between micro and macro, so around that 10 to the 3rd range. Okay, so keep those terms in mind as we continue in the course. Macro, meso, micro, nano. And, you might be thinking, well, okay, meso, that's around 1,000 times smaller. It's kind of like a millimeter, right? Well, I can visually see a millimeter on a ruler. Yeah, you can, but can you really, if something was, you had like a object that had dimensions around a millimeter by a millimeter by a millimeter, can you really analyze that in a large amount of detail with your eyes? Yeah, you could see it, but it's like a little speck. A speck of dust would be on the mesoscale. I guess you can see it, but can you really analyze it? No, right? You're going to need a zooming device. So really the macro scale is not just that you can see something, but that you can see it in all of its detail and analyze it. Can't really do that with a speck of dust, with just your eyes. Okay, chemistry, a science for the 21st century. Chemistry is the study of matter and the changes it undergoes. Chemistry is often called the central science because a basic knowledge of chemistry is essential for students of biology, physics, geology, ecology, and many other subjects. Indeed, it is central to our way of life. Without it, we would be living shorter lives in what we would consider primitive conditions, without automobiles, electricity, computers, CDs, and many other everyday conveniences. All right, so chemistry, the definition of chemistry, if someone asks you, what exactly is chemistry? It's the study of matter and the changes it undergoes. So in chemistry, we're studying the stuff around us and also the stuff that we're made of. In chemistry, you're asking the question, what exactly is all of this stuff around us made of? This matter, right? These things around us, this stuff around us. What is it? What exactly is it? Okay, that's one perspective of what chemistry is. But there's the other perspective is not only what is this stuff around us made of, but why does this stuff do the things that we observe that it does in certain circumstances? So why does water freeze and melt and boil? Why does gasoline go from a dormant liquid to then when you spark it, it has this violent reaction that gives off a lot of heat, and it turns into a gas? So chemistry is what exactly is the matter around us, and why does it act the way it acts in certain circumstances? That's chemistry. Okay, and you can see why it's called the central science, because how much more central can you get as far as you're studying what the stuff around us is made of and why it acts the way it acts, right? Biology, physics, geology, everything involves stuff. So chemistry is at the center of any physical science. Although chemistry is an ancient science, its modern foundation was laid in the 19th century, when intellectual and technological advances enabled scientists to break down substances into ever smaller components and consequently to explain many of their physical and chemical characteristics. The rapid development of increasingly sophisticated technology throughout the 20th century has given us even greater means to study things that cannot be seen with the naked eye. Using computers and special microscopes, for example, chemists can analyze the structure of atoms and molecules, the fundamental units on which the study of chemistry is based, and design new substances with specific properties such as drugs and environmentally friendly consumer products. So yeah, what they're saying is that, so chemistry, you can imagine, is an ancient science. It's probably the first ever science that was actually practiced, because wouldn't that be, if you're like a caveman or cave woman, wouldn't the first thing you would do scientifically was think about, what is this stuff around me, right? What is this dirt? What is this rock made of? What is all this? What is this air here? I can't push my hand through a solid, but I can push my hand through this kind of space around me. So what is all this? Right? So it's technically an ancient science, but they're saying it wasn't really until the 1800s, the 19th century, where chemistry really took off. And this development of chemistry was facilitated by more sophisticated technology, microscopes, computers, instruments for measuring temperature, pressures, etc. All of this allowed for the discovery of the atom, the electron, the proton, the neutron, etc. Right? What we're going to see is, as we progress through the textbook, our knowledge of why substances freeze, boil, melt, why gasoline burns the way it does, what exactly matter is made of. All of this is based on understanding things that are happening at the micro and nano scales. So prior to microscopes and just these high-powered instruments that can allow us to study and view and measure phenomena at these small scales, we were severely limited in how far we could understand the matter around us. Right? You can think about it like Isaac Newton could develop physics his laws of gravitational attraction, his laws of motion, his analysis of light, because he wasn't required to view and measure phenomena at the micro, nano, or even meso scales. You just need time measurement devices, distance measurement devices, the macroscopic distance measurement devices to measure speeds and accelerations, etc. Similar idea when it comes to geometry and even astrology to some sense. You can view the stars with your eyes. But chemistry, if you can't view and take measurements at a small scale, then you're stuck, right? So as we go through this textbook, you'll keep in mind, you'll be able to see how there's very little of this textbook that could be developed prior to the 19th century. Okay, it is fitting to ask what part the central science will have in the 21st century. Almost certainly, chemistry will continue to play a pivotal role in all areas of science and technology. Before plunging into the study of matter and its transformation, let us consider some of the frontiers that chemists are currently exploring. Whatever your reasons for taking general chemistry, a good knowledge of the subject will better enable you to appreciate its impact on society and on you as an individual. So yeah, what are some topics that are currently going on in chemistry in the 21st century? So A here, the output from an automated DNA sequencing machine. Each lane displays the sequence, indicated by different colors, obtained with a separate DNA sample. So this is DNA strings. We can visually see these DNA chains here, chains of molecules within DNA. Okay, the picture B, a graphene supercapacitor. These materials provide some of the highest known energy to volume ratios and response times. Okay, so let's see, this is more of a macroscopic scale here, graphene, and then graphite oxide, a supercapacitor. So a capacitor stores charge. So compared to typical capacitors, these graphene supercapacitors are able to hold hundreds of times the amount of electrical charge as standard capacitors. Okay, picture C, the production of photovoltaic cells used to convert light into electrical current. So solar panels, that's the physics of solar panels. Okay, D, the leaf on the left was taken from a tobacco plant that was not genetically engineered, but was exposed to tobacco hornworms. The leaf on the right was genetically engineered and is barely attacked by the worms. The same technique can be applied to protect the leaves of other types of plants. So yeah, genetic engineering, that's chemistry, right? With genetic engineering, the worms don't attack this tobacco plant here. Okay, compared with other subjects, chemistry is commonly believed to be more difficult, at least at the introductory level. There is some justification for this perception. For one thing, chemistry has a very specialized vocabulary. However, even if this is your first course in chemistry, you already have more familiarity with the subject than you may realize. In everyday conversations, we hear words that have a chemical connection, although they may not be used in the scientifically correct sense. Examples are electronic, quantum leap, equilibrium, catalyst, chain reaction, and critical mass. Moreover, if you cook, then you are a practicing chemist. From experience gained in the kitchen, you know that oil and water do not mix, and that boiling water left on the stove will evaporate. You apply chemical and physical principles when you use baking soda to leaven bread. Choose a pressure cooker to shorten the time it takes to prepare soup. Add meat tenderizer to a pot roast. Squeeze lemon juice over sliced pears to prevent them from turning brown, or over fish to minimize its odor. And add vinegar to the water in which you're going to poach eggs. Every day we observe such changes without thinking about their chemical nature. The purpose of this course is to make you think like a chemist, to look at the macroscopic world, the things we can see, touch, and measure directly, and visualize the particles and events of the microscopic world that we cannot experience without modern technology and our imaginations, right? So that's the main goal here of this course. We want to be able to look at the macroscopic world, the things we can see, touch, and measure directly, and visualize and intuitively understand these macroscopic things that we see about matter and the changes it undergoes from a microscopic perspective, because or nanoscopic perspective, because all of these macroscopic observations we make about matter and the changes it undergoes around us, the physics of why these things are happening is taking place at the microscopic or nanoscopic level. In other sciences, that's not always the case, but in chemistry, that is the case. So you want to be able to look at water boiling visually, and then in the back of your mind, you can use your imagination to visualize what's happening microscopically, the physical reality of what's happening as the water boils. That's the goal of this course. At first, some students find it confusing that their chemistry instructor and textbook seem to be continually shifting back and forth between the macroscopic and microscopic worlds. Just keep in mind that the data for chemical investigations most often come from observations of large-scale phenomena, but the explanations frequently lie in the unseen and partially imagined microscopic world of atoms and molecules. In other words, chemists often see one thing in the macroscopic world and think another in the microscopic world. Looking at the rusted nails in the next figure, for example, a chemist might think about the basic properties of individual atoms of iron and how these units interact with other atoms and molecules to produce the observed change. Yeah, so this is really common, something you're going to have to get used to in chemistry and even thermodynamics. Okay, you've got macroscopic observations and measurements that you're able to easily observe and measure. We can use thermometers or thermocouples to take temperature measurements, scales to get weights, our eyes to see colors, our noses to smell things. It's not that these are easy to measure, but they're relatively easy to measure compared to having to use a microscope to measure something, or a scanning electron microscope to look at atoms. Or like you could use a microscope to not just visualize something, but to take a measurement maybe, of a really small length or weight, let's say. But real life devices that we get patents on, devices that we use to do things, you can't easily take some sort of a measurement with like a scanning electron microscope. You can use your phone to take a temperature measurement. You can't use your phone to easily just look to scan something in like it's a scanning electron microscope and take a high precision measurement of a grain size in a metal. So what we need to do is we need to, one of the things that we do in chemistry and thermodynamics is we are wanting to make these bridge these gaps between macroscopic and the physical reality at the microscopic and nanoscopic level. How can we take a temperature measurement of something and use that measurement to state what's happening at a microscopic level? Again, because it's easy, it's relatively much easier to take a temperature measurement of something than it is to go into this laboratory and take a scanning electron microscope measurement at one region of that something. I can easily go to Lowe's right now and get all kinds of devices that will allow me to measure temperature, right? So again, it's the goal of one of the big goals of chemistry and thermodynamics is bridging that gap between what we can see and measure from a macroscopic perspective to what is actually happening at a microscopic or nanoscopic perspective, right? These rusted nails here, we can visually see the rust. That's a macroscopic observation. qualitative observation. So what we want to do is, in this course, is bridge that gap. This macroscopic visual observation, what is happening at the microscopic and nanoscopic scales that's causing this color change here, and like roughness change as well, and really the degrading of the metal. Okay, so in this next section here, we're not going to go through some of these sections in full detail. I've got separate videos and playlists that go into full detail on a lot of these topics. But the scientific method is the way we approach and systematically use our intelligence and critical thinking skills to answer questions and solve problems in science. Okay, to do this, to solve these problems, answer these questions, one of the things we do is we make observations and collect qualitative and quantitative data. Qualitative is just a visual observation. You're just making a general description of something. These nails turned this brownish red. They were left outside for a period of time, and they went from the shiny metallic color to a brownish red color, where the surface was initially was relatively smooth, and now it's this rough surface. That's a qualitative measurement. Quantitative observations, quantitative data is when you're taking measurements. You can write down something definitive about that observation. So yeah, I mean, you could write down that the color of these nails is brownish red. I guess you could do that. But really, when we think of quantitative data, we're more thinking about numbers. Qualitative observations or data is just these general observations. Qualitative data, you have to more write out as a little 2 or 3 sentence paragraph. Whereas quantitative data, it's more of you take a measurement, here's a weight, here's a number. You take a temperature measurement, a weight measurement. You could kind of think of saying that these nails are a brownish red as quantitative data. I like to think of quantitative data as if you could put it into an Excel sheet, that's more quantitative. Qualitative is just more of a general description. You're just describing to someone something that happened or the way something is. It's not systematic. Okay, now, what's the difference when you're doing an official investigation, an official experiments in science? What's the difference between a hypothesis, a theory, and a law? Okay, a hypothesis, what you can think about is a hypothesis. So you want to investigate something. Let's say in the 1800s, you're trying to study matter. What you're trying to see what matter is made of. Is it these individual particles, or is it just some kind of continuous fluid medium? You want to investigate. And you investigate by collecting qualitative and quantitative data, by doing experiments. Okay, a hypothesis is, so you can think about this as when you're initially doing your investigation, you collect some data, you analyze it, kind of sort of turn it into information, and based on that data, you come up with what we would call in a more casual conversation, we would say you come up with a theory. But I don't want to say theory because in science, in the scientific method, theory has a much different definition than what we use the word theory for in casual conversation. Okay, but you're initially doing your investigation. You're trying to study what in the 1800s, study what matter is. You do some experiments. You collect data. Let's say you do five or six different experiments. You collect some data. You analyze it, and from a casual conversation perspective, you come up with a theory. You say, well, okay, well, this data is saying that, and you know everything I observe is saying that matter is composed of these indivisible elements, right? These building blocks. That's your theory. Okay, this is a hypothesis. It's called a hypothesis because so you can prove your statement, your theory you made, right? This statement you've made, you can prove it. You can say, look, here's the experimental results. This happened, and there you go. my theory, my explanation is validated by these experiments. Or you could maybe disprove the hypothesis. Maybe you could make a hypothesis and then either you or other people do more experiments and the hypothesis gets disproved. So what a hypothesis is you can think about it as when you start an investigation into something. It's based on the initial data and experiment. You're making statements about what you believe is going on. But these statements it's not like you have to worry about being right or wrong. They're just statements that you throw out there and you say, okay, I or other scientists are going to investigate this hypothesis further and see if we can sort of prove or disprove the hypothesis. Where it doesn't matter if it's proved or disproved. You're just going through the investigation, right? It's like if you were a criminal investigator, you might make some initial observations and your hypothesis is, okay, I think this person was involved. The initial information I've gathered, just we interviewed this guy, he was kind of sketchy. I think he's involved. It's a hypothesis, though. You need to gather more evidence. Other people are going to look into it, and that hypothesis might be proved or disproved. Okay? Now, in science, if you have a topic that's being investigated that gets promoted to a theory, that's the closest that anything in science can get to being a fact. From the perspective of science, there are no facts. Okay, so a theory, today we have atomic theory, right? When you talk about matter is centered around atomic theory. It's a theory. It gets promoted to a theory after there's many hypotheses that are saying that, okay, matter is composed of atoms, and these just keep getting proved over and over and over again from different perspectives. Different experiments, different scientists are validating the hypotheses that are saying that matter is made up of atoms. And so at some point, there's so many validated hypotheses that it gets promoted to a theory. Okay, but why is it called a theory, though? Why isn't it called a fact? Well, because we can never know something with 100% certainty in life, right? It's like, okay, are you watching this video right now on YouTube? I mean, yeah, that's as close to a fact as you can get, that you are, in fact, watching this video. But is it really a fact, right? What is truth? What is reality? For all you know, like they talk about in terms of wormholes and whatnot, you could be in multiple places at once right now. We don't know. In 500 years, maybe once we've studied quantum mechanics in extreme depth, maybe viewing matter from the perspective of atoms, we learn is not the best perspective to use. It's a theory, right? No one has ever seen an atom with their eyes. It's only through the aid of microscopes. No one has ever actually seen an atom with their eyes. But even if they did, okay, well, what is vision? What does sight even mean, right? It's all theories. Only God, the creator of the matter around us, has the facts. Now, what about a law? What is a law? A law is it's the parallel to a theory, but from a numerical perspective. So like a theory is more qualitative, whereas a law is more quantitative, with theories and laws being as close to fact as we can get. Newton's laws of motion. So Newton's second law, F is equal to ma. It's just a law is something that you can, it's like a theory, but that you can put numbers to. You can do calculations with. You can take measurements with. That's all a law is. Whereas a theory is just more of an abstract description of some phenomena in nature that has been validated extensively by proven hypotheses, and that kind of everyone is in agreement with. Classifications of matter. We defined chemistry in the opening section as the study of matter and the changes it undergoes. So what is matter? What exactly is matter then? Matter is anything that occupies space and has mass. Matter includes things we can see and touch, such as water, earth, and trees, as well as things we cannot see and touch, such as air. Thus, everything in the universe has a chemical connection. So this is a little bit confusing because we know with Einstein's developments, with formulas like E is equal to mc squared, like energy is matter, matter is energy. With quantum mechanics, you start to think about what is matter. Matter is waves. Matter is particles. Again, is matter and energy or interconnected, right? Okay, so in the year 2025, matter is exactly what they described here, which is if there's anything in the universe that even to the tiniest extent at the nano scale or smaller has a mass, which means it is subject to the forces of gravity, and it takes up space, which in the year 2025, from our perspective, you can't have mass without at the same time taking up space, right? Then that's what we call matter. And even though, we think about, well, what is matter, and is matter and energy the same thing? Because energy is not matter. The way we view this is if to some extent we can either macroscopically or with high-powered instruments find the weight of something, which is going to intrinsically mean that we're going to think about it as taking up space as well, then that's what we consider matter. Light, electromagnetic radiation, we would not consider matter. Why not? Because we can't weigh light. I mean, yeah, I guess it takes up space, but not really. I can bring light into my living room, and it's not interfering with the space I have at all. Again, you can't. We don't measure the weight of light. There's really no conventional sense in the year 2025 that we ever think about measuring the weight of light. Electrons we do. Protons we do, but not light. So light is not matter. It doesn't have a mass or a weight. But in general, we don't think about light as being affected by gravity. Even though, according to Einstein's theories, light is in space affected by gravity. So it is a little bit ambiguous, kind of confusing. But in the year 2025, we don't view light as matter. Okay. Chemists distinguish among several subcategories of matter based on composition and properties. The classifications of matter include substances, mixtures, elements, and compounds, as well as atoms and molecules, which we will consider in the next chapter. Okay, so yeah, how do we categorize matter around us? So, okay, first is that there's matter that we refer to as substances, a substance. This is a form of matter that has a definite, constant composition and distinct properties. So the way you want to think about a substance is it's anything that's not a mixture in any way. So when it comes to a mixture, you can have a homogeneous mixture or a heterogeneous mixture, to where a homogeneous mixture it's like when you dissolve salt or sugar in water. The salt and sugar molecules, they don't clump together at all. They get completely dissolved. They get surrounded by the water molecules. However, there's no chemical change that takes place with a mixture. The sugar molecules are still just sugar molecules. They just declumped. The salt, I guess it kind of undergoes a chemical change. They break up into the Na plus and Cl minus ions, but no, we still consider that there's no chemical change involved. Whereas with a heterogeneous mixture, there's no kind of breaking up of the molecules from clumps and getting evenly distributed and surrounded by the solvent molecules. It's just like spaghetti. You've got noodles and sauce and meatballs all mixed together heterogeneously. All right, so anything that it's not a mixture, any matter that is, you would not consider it a mixture, you could call that a substance. It doesn't mean that it has to be composed of a single type of atom, like just carbon, just hydrogen. No. As long as it's not you wouldn't look at it as a mixture, a homogeneous or a heterogeneous mixture, then you can call that a substance. Water, ammonia, table sugar, gold, oxygen. Okay? Whereas if you combine two or more substances together, mix them together, but there's no chemical change that takes place, it's just a pure mixing, then you call that a mixture of substances. To where, once again, you've got homogeneous and heterogeneous mixtures. Okay, now, when it comes to substances, we can further subcategorize substances. We can break substances down into elements and compounds. Okay, an element is a substance that cannot be separated into simpler substances by chemical means. Okay, so when we think of elements, we typically think about the periodic table of elements. Okay, but in general, it's an element is more than just what you see in the periodic table. An element is any substance that is composed of just one type of atom. So oxygen gas is composed of O2 molecules. That's an element. That's the element oxygen. Gold, you've got this crystal structure of gold atoms. It's this one type of atom. That's the element gold. And it's saying you can't separate those atoms into simpler substances by chemical means. You have to use nuclear means. So by chemical means, they're just referring to, sharing and transfer of electrons. That's chemistry, chemical reactions. You have different atoms, and they can transfer, share electrons, and kind of break up from that perspective. But anything further than that is not chemical. You're going to have to get into the nucleus, breaking up the nucleus. That's not chemical. That's nuclear. So an element, since it's composed of just one atom, one type of atom, there's no way to break it down any further by just ordinary chemical means. If you're going to go further, you're going to be getting to that nuclear realm. Whereas a compound is a substance composed of atoms of two or more elements chemically united in fixed proportions. So it's not just two or more elements, because you could potentially have a mixture of two or more elements, like carbon and steel, for example. So it's a compound is specifically, it's composed of two or more elements that are joined chemically. There's bonds, chemical bonds, sharing or transfer of electrons going on, like sodium chloride, for example, an ionic compound, H2O. You can break down a compound into simpler proportions, simpler pieces of matter, using chemical processes, just breaking these bonds between electrons. Okay, but if you don't have two or more elements, you have to have two or more elements composed in a compound, or else it's an element, not a compound. Okay, and so that's it. If we look here, this is how matter is completely classified. All of the matter around you that you ever have interacted with in your life, and you ever will interact with in your life, can be categorized just like what was just described. You could look at any matter and say, okay, it's either a mixture or it's not a mixture, which means it's a substance. Again, if it's a mixture, you've got these different types of elements sort of put into the same package, but there's been no chemical interaction between those elements. Carbon and steel, salt and water, sugar and water, spaghetti and meatballs and noodles. You just mix them together, but there's been no chemical interaction between the different types of matter. That's a mixture. So you're either, when you look at matter, any kind of matter, you're either looking at a mixture, or if it's not a mixture, it's a substance. Okay, and with mixtures, you've got homogeneous mixtures and heterogeneous mixtures. Okay, now with substances, you've either got what you could think about as a mixture of substances, but it's not a mixture anymore. That would be a compound. You have two or more compounds together, but they're joined together by chemical means. Or you have just one type of atom or element, and you call that an element. So compounds can be separated into elements using chemical methods. And also you can note that mixtures are separated into substances by physical methods, like distillation, the distillation process, for example, or filtering, right? When you filter something, you're separating, like water and pasta, right? You're filtering it. Okay, now matter around us, when you observe matter around you, what we all know is that matter can be in one of three states. There's more states than that. There's at least a fourth state, but in general, from our typical observations, we observe matter as being in one of three states: a solid, a liquid, or a gas state. All right, so all substances, at least in principle, can exist in three states: solid, liquid, and gas. Yeah, so in principle, any substance, even mixtures as well, but just to think about this generally, we'll just say substances, are able to exist in a solid, liquid, or gas state. You can evaporate metal. Absolutely. You can condense carbon dioxide gas to a liquid or solid. Okay. As figure 1.6 shows, gases differ from liquids and solids in the distances between the molecules. In a solid, molecules are held close together in an orderly fashion with little freedom of motion. Molecules in a liquid are close together but are not held so rigidly in position and can move past one another. In a gas, the molecules are separated by distances that are large compared with the size of the molecules. Yeah, so in a solid, the molecules are rigidly held together in like this orderly fashion, and they don't have much freedom of movement at all. Okay, in a liquid, the molecules are still constrained. They can't kind of go wherever they want in one sense. They can slide past one another and go wherever they want, which they couldn't do in the solid, but they are constrained in the sense that they have to stay together as a body. Okay, whereas with a gas, now the molecules are fully free. They can go wherever they want, and the only reason they would stay together as a body is if there's a container that constrains them. Okay, the three states of matter can be interconverted without changing the composition of the substance. Upon heating, a solid, for example, ice, will melt to form a liquid, water. The temperature at which transition occurs is called the melting point. Further heating will convert the liquid into a gas. This conversion will take place at the boiling point of the liquid. On the other hand, cooling a gas will cause it to condense into a liquid. When the liquid is cooled further, it will freeze into the solid form. So yeah, when you convert between the states of matter, these are physical changes. You're not changing anything about the chemistry or the composition of the matter. Even with mixtures, you can take mixtures and think about melting them, boiling them as mixtures. So you can convert between the states of matter without changing the composition of the matter. It's these pure physical changes. The states of matter are purely physical, not chemical. Okay, so here they show a scenario where you've got water in this same system here in all three states. You've got water vapor here in the gaseous state, ice water in the solid state, and liquid water in the liquid state. Right, but you can see as far as chemically, there is no difference. It's just water molecules in all three states, H2O. Now they point out that, we're going to learn more details about this later, water is very unique, and this is one of the reasons why we can even exist as human beings on Earth. It's unique in that solid water is less dense than liquid water. You can see these are more spaced out. That's why ice floats. You can think about that. That's very unique. In general, for materials, elements, compounds, that the solid state is going to be more dense than the liquid state of a compound. Okay. Physical and chemical properties of matter. So substances are identified by their properties as well as by their composition. So when you're looking at a substance, an element, substance, whatever, even a mixture, you can identify that matter by its chemical composition. Is it H2O? Is it NaCl? Okay, but matter, it doesn't just have a composition. Matter also has properties, physical or chemical properties. So color, melting point, and boiling point are examples of physical properties of matter. A physical property can be measured and observed without changing the composition or identity of a substance. That's the essence of a physical property. You can measure or observe it without changing the chemical composition, what the matter is composed of, which another word for that is the identity of the substance. When you smell something, when you look at the color of something, or the boiling point or the melting point, which just refers to changes of state of something from the solid, liquid to gas state. For all of these properties, you're not compromising what the matter is composed of in terms of the types of atoms, as well as the way that they're bonded to each other. More importantly, the way that they're bonded to each other. You're not changing any of the chemical bonds. Okay, for example, we can measure the melting point of ice by heating a block of ice and recording the temperature at which the ice is converted to water. Water differs from ice only in appearance, not in composition, so this is a physical change. We can freeze the water to recover the original ice. Therefore, the melting point of a substance is a physical property. Similarly, when we say that helium gas is lighter than air, we are referring to a physical property. If you want to weigh something, that's a physical property. On the other hand, the statement hydrogen gas burns in oxygen gas to form water describes a chemical property of hydrogen, because to observe this property, we must carry out a chemical change, in this case, burning. After the change, the original chemical substance, the hydrogen gas, will have vanished. And all that will be left is a different chemical substance, water. We cannot recover the hydrogen from the water by means of a physical change, such as boiling or freezing. Yeah, so the only way to make the statement that hydrogen gas burns in oxygen gas to form water, to observe this, you have to carry out a chemical change. Hydrogen gas burning in oxygen gas, you're changing the bonds of the atoms, the elements. You start with hydrogen gas and oxygen gas, and then you're left with water. That's a chemical change, and chemical changes are associated with chemical properties. A property is just a characteristic of a substance or matter. If to observe or measure that characteristic, a chemical change needs to happen, because how else would you observe or measure it? How would you, if you want to measure the heat given off during the burning of hydrogen gas, how else would you measure that other than carrying out this burning process? Okay, so a chemical change needs to occur, then that's a chemical property associated with a chemical change. And then the same idea with physical properties, physical changes. Every time we hard boil an egg, we bring about a chemical change. When subjected to a temperature of about 100 degrees Celsius, the yolk and the egg white undergo changes that alter not only their physical appearance, but their chemical makeup as well. When eaten, the egg is changed again by substances in our bodies called enzymes. This digestive action is another example of a chemical change. What happens during digestion depends on the chemical properties of both the enzymes and the food. So yeah, it's really, you have in nature, in life, you have chemical changes and physical changes. Things that take place chemically or physically. Okay, if you're going to measure something, a property of something, if it's associated with that chemical, a chemical change, then it's going to be a chemical property. If it's associated with a physical change where nothing chemically is taking place, just pure physical phenomena, then it's going to be a physical property. That's the idea. If you want to measure anything associated with digestion, directly associated with digestion, that's you're measuring a chemical property. Because when the food, when you intake the food, it gets broken down. All the chemical bonds are being broken down. All measurable properties of matter fall into one of two additional categories: extensive properties and intensive properties. So these physical and chemical properties can be extensive or intensive. Okay, the measured value of an extensive property depends on how much matter is being considered. Mass, which is the quantity of matter in a given sample of a substance, is an extensive property. More matter means more mass. Values of the same extensive property can be added together. For example, 2 copper pennies will have a combined mass that is the sum of the masses of each penny, and the length of 2 tennis courts is the sum of the lengths of each tennis court. Volume, defined as length cubed, is another extensive property. The value of an extensive quantity depends on the amount of matter. Yeah, so an extensive property is going to depend on the amount of matter you have, okay? As opposed to an intensive property is not going to depend on how much matter is being considered, like density is the best example. The mass of an object divided by its volume. The density of steel doesn't depend on how much steel you have, right? You can have a huge beam of steel or a steel ruler that you could hold in your hand. Both have the same density. They have different masses because mass depends on the size, right? How much is there? But the density of steel, it doesn't matter how much steel you have. The property is not dependent on that. Now there is temperature, right? Temperature, it doesn't depend. The temperature of something doesn't depend on how much of that object you have. You have a big, huge pot that's really hot, or a small pan that's really hot. If they're at the same temperature, it's going to have the same result if you touch either one of those. If they're at the same temperature, right? It doesn't matter how much of the big the pans are, the pots are. Suppose that we have 2 beakers of water at the same temperature. If we combine them to make a single quantity of water in a large beaker, the temperature of the larger quantity of water will be the same as it was in 2 separate beakers. Yeah, so unlike mass, length, and volume, temperature and other intensive properties are not additive. That's a feature of intensive properties that is not a feature of extensive, or that's a feature of extensive properties. That's not a feature of intensive properties. Extensive properties are additive. You take the mass of one thing and the mass of another thing and put them together, you can add the masses. It doesn't work that way with intensive properties. If I have a pot of water and the water's at 90 degrees, and another pot of water and the water's at 30 degrees, it's not like you put them together and you add the temperatures to get the new temperature. I mean, yeah, there is going to be sort of like an averaging effect there, but it's not like you're going to say, oh, okay, this water's at 70 degrees, this water's at 30 degrees, or 40 degrees, it's not frozen. Put them together, the temperature's going to be 110. No, of course not. Okay, measurement, units and measurement. So I've got an entire playlist. It's in the works right now, but by the time you're watching this video, it might be fully complete. There's an entire playlist that goes into full detail on units and measurement. It's a really good playlist. I'm excited about it. I think you're going to find it very useful and interesting. So, and it applies to all subjects in science and engineering. It's just a general units and measurement playlist. So go check that out if you need before getting deep into this playlist. Volume, density, temperature scales, we talk about all of this. Okay, scientific notation, significant figures. These topics all have their own dedicated videos and playlists on the channel. So go check out those videos if you need. Okay, dimensional analysis in solving problems. So here they're just talking about things like unit conversions and working with dimensions in problems, making sure your dimensions all match up. So this is another topic that we talk about in detail in the units and measurements playlist. This is a very important topic. So go check that out if you need, but you'll also get the hang of this as we solve problems, work example problems, and just as you get more experience with problem solving, right? So like here, it gives tips for problem solving. We're going to learn this as we progress through this playlist and other playlists, right? Critical thinking, skills, tricks, techniques. We're going to learn in real time as we progress through the course and work example problems and read the textbooks, talk and reason through problems.